I get one project for you. I want you to give a project presentation, 5 minutes, about what according to the comment I make, right? So that I make sure that your team can have some preliminary result and 5-minute presentation next week, right? So that I know we almost reached the end of the semester, so that it's time to let your student to give some discuss about this kind of vibration engineering. Okay, so it's something 5 minutes. It's you don't need to spend about your project for 1 hour or something. Okay, of course. Last time we also mentioned about the some issue of the project. So I hope that you if you have some additional problems for the project, of course I give you some advice. So again, there are two projects, right? First is relate to this kind of amendship, this kind of engineering, so that in this case, from my point of view, I remember you probably got this kind of 3-dimensional model from the company, the engineer, right? The DWG, so that you need to how you can construct this kind of 3 degree of freedom model. I don't give you any idea how can we? You have the engineer give you the design, right? How can you use this kind of design, 3-dimensional drawing to construct this kind of simplified model? How? Hey, this is important now. You need to think about how to use what discussed in the past almost 1 semester now. How can you do? Do you have an idea about this thing? Actually, I try to create some here, so that I think they give this kind of 3-dimensional design, right? Like AutoCAD, right? So how can we build simplified model? How? Any idea? How? This is real product. I'm not talking about some example in our lecture example. How can you create simplified 3D feeder model? We described some method already, Any idea how? Basically, this is they give you this kind of computer this kind of model, 3D model, right? In AutoCAD or DWG. So how can we create similar model? Hey, you cannot say you forget about what we have discussed. In the chapter of multiple degree feeder system, how I did tell you, inference coefficient method, what is that? We described about some simple this kind of beam problem, and then so this is exactly about this geometry is more complex, but it is. Remember we talked about this 3 degree feeder. For example, you have beam, right? And then we have a loading. So basically, if you have 3 degree feeder, basically you apply some kind of loading force, maybe P1, 2, 3, So you basically you try to apply the loading, but in the ASICs or commercial FEM software apply some loading force, right? And then measure displacement. That's something you can do this thing, right? So basically, it's not using those assignment, but you try to apply the loading, right? Basically, we describe, But of course, this is something is practical. So if you apply this kind of 1 Newton, 0, 0, the same thing, right? I mean, you apply some loading force, 1 Newton force. Right? You define the 3 degree freedom thing. Of course, first it describe for this ship, right? What's the degree freedom you describe? 3 degree freedom. Right? You need to describe it more precisely. Okay, the certain kind of vibration, right? Downward vibration, because in general, a ship is what? 3-dimensional. So that if you want to simplify, then you may think about, okay, what's the dominant motion of this ship, right? So that if it is more slender, and then most likely, if you assume this thing, then maybe that's something you may think about minimum degree of freedom issue as I mentioned, right? So that what thing? So that x1, x2, so that maybe at least this kind of thing, right? It is enough, and then plus additional x1, s2, and now s3 is this direction. Or maybe you also need to describe additional rotation. That's a thing. So that's another important thing. When we look at the vibration engineering, we need to focus on most critical issue of what kind of motion variable, displacement, linear displacement, angular displacement, what the more thing we need to care, so that then we try to set up that kind of vector, right? That means x1, s2, or something, minimum degree of freedom, and then to describe the critical issue of this product. Mechanical system, they can conquer the problem. So this is the thing. Of course, I already mentioned, right, in our previous lecture, so that typically the important thing we care most likely for the ship engine. We need to describe the vibration engine, because this is one of the dominant the source of vibration, right? And then you have additional this kind of propeller or thing, and then some transmission. So it is there's certain kind of critical, right, vibration issue we want to describe in more precise way. That's why it's not randomly we pick up. So actually, this is actually even more important, right? How you choose this kind of where to describe the vibration of this kind of real product. I think it's a matter how you define the engineering problem, vibration problem. You specifically there you try to really describe. Then of course that's why I give you some reference, right? If you look at previous that's kind of the project with Yunzhou Tech, so that they at least show you some important issue to think about vibration for this kind of main ship. Okay. Anyway, so the key situation is you need to first step probably you need to describe, right, those kinds of xi, right, vibration at x1, 2, 3, and the location. This location of this step 1, and then next one is step 2 is what? Then one define saying, then you apply we have chapter, right? Inverse chapter 6, right? And degree freedom, this kind of the way, the method to do this kind of thing, but using this kind of FEM software, right? FEM software to do this kind of thing, right? That when you apply, for example, how we define our basically we are trying to define our MCK, right? We have certain kind of MCK, right? And CK, and then okay, this is 3 by 3, right? And this is 3 by 3, okay? So that we need to use our software, right? And then in the software, FEM software, maybe ANSYS or SolidWorks, right? Import this thing and then apply some loading to determine our KIJ. Determine our KIJ. What is our KIJ? We already discussed thing, right? It might mean you apply KIJ we define in our undefeated model is what? I hope still remember what was it? F equals KX, right? So that there's a way we try to apply some simple way I can try to simply analyze this kind of thing, right? We define KIJ, or sometimes we look at the A is X, right? So that the inverse of spring constant is A, flexibility. So it is in our undefeated model, we told you about two approaches. Stiffness input coefficient and flexibility input coefficient. But in reality, I guess one method may be better. If you look at FEM, so that most likely probably apply the loading force will be easier. Do you understand? So in FEM, you can build this kind of model, apply loading, determine displacement. So that in this case, most likely, I guess this kind of flexibility coefficient will apply the 1 Newton force, and then so that I can say OA equals X here. Is that apply the 1 Newton force, and then I measure displacement, and then this is the A. Right? So of course, if you have an undefeated model, so that just slightly change this kind of AIJ. AIJ, so that in this case, that we describe in our undefeated method. Yeah. I don't know, do you have any question? This is just make sure that you have to remember what we describe in this kind of a problem in our lecture note, right? So that we do describe all these things in real person, but well, somehow if you don't carefully study, then you may forget. Let me quickly bring that chapter. Oh, this actually I do have some example, right? Chapter 6, right? So that so you basically you try to do the kind of thing. Mosaic is AIJ, right? AIJ, but we show you. We show you. Basically, we'll show you about how we can try to solve this thing. Right? Just try to, but this kind of thing now it's not using the UG sound, okay, but using FEM software, I can do this kind of modeling. See, just similar thing, okay. So that apply some kind of loading force, and then we try to determine the kind of AIJ, and then in this case, one different AIJ, and then I try to do the inverse of this A and get the different matches. Is there any question? Let's repeat this thing, but in those commercial FEM software. Of course, I do have. I do have this kind of lecture note talk about FEM. Probably I should also quickly show you this kind of what is FEM? Finite element method. So FEM, of course, you have probably used commercial software, but let me quickly show you about basic principle FEM. Right? Basically, it's the key idea of FEM is what? We discretize very complicated problem governed by the PDE, partial differential equation, in solid mechanics, fluid mechanics, or more general problem, or electrical system like our micro machine. And then so that then we try to think about how we can build an element, a discrete element based on kind of mathematical analysis. Okay, so what is FEM? Sometimes they call FEA, finite element analysis. It's some kind of mathematical way, mathematical method, I would say, to get approximate the numerical solution. Right? So that we derive in our current thing. Basically, we try to discretize maybe one-dimensional vibration model we learned in our previous chapter. Remember, vibration of cable, vibration of being with n degree the n go to infinity. So that this is thing. So this kind of FEM have been widely used originally from sound mechanics, then apply for electric engineering, microelectronics, and civil engineering, thermal engineering, and also our micro machining technology. Yeah, so it becomes a very important tools in the industry. Of course, there's a series of software. Basically, for our mechanical pattern, you see, you have this kind of geometry, like our Intel-Tech unmanned ship, apply the loading, and then we discretize this kind of three-dimensional, very complicated product model into discretize, maybe 3 elements. So this a triangular element. Use this kind of a finite number of elements to build, to describe this kind of more complicated 3-dimensional design of your product. So this is something I just tell you, right, from real continuous model to this kind of a discrete model with finite. The key thing here is a finite number of this thing, right? Finite number of this element. Is that right? FEM, right? Finite element. Why? Because discrete. Originally, we have the very complicated the problem and the continuum. So this is one thing. One thing discretize. What does it mean? That means that we turn very complicated mathematical problem, like partial differential equation, into ODE. That's something is much easier we can solve, right? So most likely the continuous problem is by PDE, partial differential equation, and then discretize, and then we become ODE. So that's much easier ordinary differential equation, So this is equations. Okay, most time is I think that is something much easier we can solve. Yeah, PDE partial differential is much more complicated. Hey, I don't know if our UG programs study the best in PDE basic. No. Oh, okay. But at least in our vibration of being or cable, as introduced, that the equation, common equation, or equation motion is PDE. Vibration of cable, vibration being, actually is a PDE, partial equation. So that, I see. But anyway, unfortunately, many of our mechanical engineering we deal with the real engineering problem is PDE, partial, that is difficult. Differential equation, this is a difficult part. And then so that's why this is much easier we can solve. Our MCK model, undefeated basis is ODE, yeah, but a different way to do discretization. Okay. Okay, and so that of course this has a basically easy. We have different way to construct this finite element. Three node triangular or or this kind of thing for 2D structure or 3D structure, so that the different kind of this kind of element would construct, right? So that this is a typical, right, thing in used in all the commercial software, right? And then so in this case we try to describe, right? Originally, you see, if it is construction, and then for each element we describe there, of course, equation motion, right, in linear and angular motion, and then of course in this case make sure when we solve this kind of so many equation motion for each element, and make sure it's compatible. Right, if it's not compatible, and then you can see this will be broken, right? So that it's not realistic, right, for real deformation of a 3-dimensional structure. So this This is when you try to construct this kind of equation motion for each element. We are consider about equation motion, consider about equivalent condition and compatibility condition, okay, and bound condition. Yeah. So these are basic things we do. And then of course, eventually, most likely when we do this thing is we try to describe this kind of a spatial displacement field as this kind of linear combination of x, y, or x, y, z. So I describe this thing, right, for each element. So this is something is important. We use this kind of simple polynomial like function to describe the displacement of each element, right? And of course, the key thing here now, how I determine this A1, A2, A3 based on some mathematics formulation. So this is a key thing, right, to build this kind of we call finite element, this kind of model. So that here, so of course, once you can create a step of this kind of matrix for each element and they assemble into the big, this kind of this kind of equation, right? Linear algebra equation, they can solve it, right? Of course, if you consider time dependent model, and then you also introduce your matrix, right, or math matrix here. So this is a very basic way introduced. And typically, why this become so popular in the many years since 1950, because this method has a good advantage compared with the other. We have other method, discretization. For example, finite, FDM, finite difference, finite difference method, and also boundary element method. There are several ways to solve this kind of a very complicated problem, but FDM is still one of most popular method to treat for our engineering problem in mechanical engineering, aerospace engineering, electronics, semiconductor, and civil engineering. So it's something. I think the good thing here is you can have a very irregular boundary and different kind of loading, material bound condition, and then so they also solve. So it has many different advantage compared with the other method, I would say. Yeah. And then of course, there's no perfect method, right? So that in general, this is approximation of the real kind of a continuum model, right? And then the second problem is element dependent solution. So that if your mesh model is not carefully optimized, then some of this kind of result may be dependent on the shape of this kind of finite element you created, right? So they still have similar issue for this kind of FEM, right? And then of course also induce some of the error in numerical solution. But in general, still, I think in many years now, so that I believe many of the problem FEM have been solved, right? That's why we continue to see so many cancel away one. Okay, so FEM basically is in 1940-50 is what most likely is used for those engineers to solve some practical engineering problem for mechanical engineering as well as engineering, right? So that anyway, so there are several key people try to gradually develop kind of mathematics method to discretize those problems in solid mechanics, and then gradually see so that if gradually more mature, then even the company Boeing try to use this one to see for design of data wing in aerospace engineering. And of course, gradually there's some very famous this kind of researcher professor or something. They gradually improve this one. In particular, this one of Professor R.W. Croft. So that he actually is one of quite famous this kind of researcher to improve this kind of FEM method for practical engineering. So anyway, so that I tell you, so that at this moment, I would say more or less this method has been mature, right? Mature, and there's so many software you can use. So that here I show you, you see, there's a long list of this software. Ergo, NC, Console, Abacus. Traditional in our ME, when I was student, ANSYS over there, Abacus. These are quite popular in our mechanical engineering. But in other engineering, sometimes they use different kind of FEM software. For example, in building engineering, structural dynamics, in civil engineering, they should use ETABS. This is something more on civil engineering, design the building, design some bridge. In China, use PKPM, developed by China Academy of Building Research. And of course, recent year, cloud computing online, same scale, the one, you don't need to download the software. You just register account online. You can do the FEM online now. So that the cloud computing is become another possible new method now. So that you don't need to download software online. So that is the technology now. So that you can see this thing. I just show you some cases, right? So if you look at this kind of online, this kind of cloud computing platform for FEM, basically it's really have some more sophisticated now. You can see they have able to solve a series of problems in different mechanical engineering aspects, fluid mechanics, sound mechanics, vibration, and actually pretty sophisticated this kind of way to study this kind of thing. Do you say so that I would say, see, vibration of V, okay, and vibration of this thing, so that that's pretty sophisticated this online software now. You may want to consider this kind of thing for a try. And here I show you one example. See, we do model analysis of kinetic rod of engine, right? And then we discretize very complicated 3D structure of the kinetic rod for the engine, right? And then the first mode of bending mode, just like 1D bending, like a beam bending. Second mode is twisting. In more three-dimensional, like a structure for the product, so that you have a combination of a different vibration mode. And here is also analysis, model analysis of flywheel. So the flywheel is a quite important also a mechanical structure, right? For engine. And then first mode, second mode, fifth mode. So you see, it's once you're three-dimensional, the kind of mechanical structure, and then your vibration can be complicated. And of course, I'll show you model analysis of a guitar, right? And then show you first neck bending mode and neck lateral bending mode, body breathing mode. You see, so that they at least show you some representative this kind of FEM result and give you some sense about how we can try to do this kind of analysis. Of course, in FEM we can solve both free vibration problem or full vibration and also static problem. All right, so this will give you. So basically, this is what free vibration problem. Why we don't free vibration is no apply loading and study the connection frequency vibration mode. Right? So that this is what this kind of FEM can do. And of course, here I show you more realistic this kind of FEM for this whole machine. This is something will be interesting for you to look at this kind of product, right? A real product, vibration impact table, and then how we can create this kind of model and then estimate the frequency, measure frequency, things like that. Of course, we also show you this kind of thing if you use it for our micro machining, or micro machine, you can sensor actuator. So micro gyroscope, osmometer, and then once you build the kind of the model in computer, and then you can study electrostatic actuation, and also look at the frequency response and electromechanical response for this kind of a sensor actuator. Anyway, so I told you there are many different things. Of course, the key thing here is as a user, right? I didn't ask you, you have to write your own FEM, right? But as user, at least you understand how we can use properly this kind of software to solve some practical vibration engineering problem. That is an important thing. Of course, in all the FEM software, basically is but still it's necessary. I quickly show you how we can really build this kind of FEM from scratch, right? So that you can see this example, right? For this three-dimensional, this kind of thing, the milling machine, right? So that in general, what do we have? We're quite complicated, thing, right? So that in this case, we define the coordinate system X, Y, Z, and then also describe those kind of the node, right? So element and being, I mean, we can use certain kind of different element, right? To for this is more on 3D or one-dimensional structure, so the being element here. But for this part, it's close to two-dimensional structure element, so it's a plane, right? So that you can see we can use different kind of element to construct this kind of more complicated three-dimensional this kind of product, right? And then of course for each node, we have described their corresponding the kind of a displacement, right? Displacement can in general it can be three-dimensional, right? Not U, W or something. They're three-dimensional. This kind of a thing to describe this thing. So that is something three-dimensional. Yeah. Of course, I told you in general we may for practical engineering. Sometimes I tell you we also be careful. Don't try to make it very complicated. This kind of model in the beginning. Make sure you can capture dominant behavior, so that in general, as I show you that we use this kind of discretize, right? This kind of displacement of x, y at one time when discretized into this kind of shape function and another time dependent function, right? And then you construct some kind of kinetic energy, right? And then we and potential energy, in strain energy in the spring and mass, right? So that once we can calculate this kind of energy, and then next one is we try to think about how we construct this kind of and until freedom mass matrix and different metrics, and we somehow loading. So that is something we of course, as I mentioned, so that this approach is what we call Lagrange equation motion. So once you can define the energy, right? Energy is stored in kinetic energy for each element, potential energy in all the elements, right? And then we, based on Lagrange equation motion, actually we can try to get the this kind of equation motion now for one element. So this is something I think is at least give you some basic idea. I think we mentioned this Lagrange motion, right? Equation motion. It's because sometimes I told you Newton's law is good, but what problem Newton's law? sigma, you know, if you have one or two elements, that's okay. You can write down all the equation motion. But if an element is go to 1,000, 1 million, are you going to write down 1 million equation? Huh? This is the thing. The range equation motion, this have systematically to show this kind of equation of motion without write down each individual. That thing, right? Do you mean? Once you get T, kinetic energy, KE, Y, and potential energy, V, PE, Y, so that then we calculate our like mv square 1/2 kx square, so that we calculate L equals T over V. Why? Lagrange equation motion is what? Basically, it's here. Minus here equals 0. And I equals 1, 2, 3, depending on degree of freedom. So that basically, you see, this gives you easily one equation, and then you can easily now can program actually. You have an undifferentiated equation motion. All the no matter how complicated kind of your product or three-dimensional structure for your mechanical system, you as long as you can calculate our kinetic energy, potential energy, then automatically I can write down our equation motion. If you use Newton's law, my God, 1 million element write down quite many equation of motion, and it's very difficult. So that is important thing why we describe this one. I think in early chapter 1, 2, 3, I do describe this kind of thing, right? So that this is something useful and important. That's why actually I also derive this kind of thing for the vibrational beam problem. Oh, let me quickly show you some simple one-dimensional element for bar. Well, if a vibration of a longitudinal loading bar and describe displacement as A plus B x, right? Apply the bound condition on both sides, right? And then the key thing here is we need to describe this. How can we describe this kind of A and B, right? So that this actually can be done. Basically, is this kind of shape function is one. That means if we get two nodal variable, right, any kind of displacement inside the bar. Basically, this is U1 and U2. So for the displacement at certain location X here, basically is what? It's a linear combination of this U1 and U2. This is based on this kind of shape function. This is called shape function here. So this is the way U here depends on nodal variable and linear combination of them. So this is the basic idea. And these are orthogonal. Okay, these two shape functions are orthogonal to each other, so that they can be useful. Yeah, and of course, once here, then we can calculate our kinetic energy. Right, so 1/2 mv square of 2 differentiation. The same thing for potential energy. Right, and then in this instance, then you can see this is what we should write. This is the M for this bar, one-dimensional bar element, right? Once you calculate this kind of strain energy, and then we can construct. Okay, now this is the final element for the bar element. Okay, so that I just quickly introduce this kind of a basic concept, right? And then so that of course there's another method is using the virtual rock function, right? This is another approach we can try to introduce this kind of thing, and then get this kind of principal virtual world. But in general, now I show you, we have a way to discretize vibration of a one-dimensional bar element in this 2-degree freedom. This 2-degree freedom finite element. Okay. Basically, this is 2-degree freedom of finite element. Right? Model. Right, for the bar. Okay, so that's something I just give you this thing. Of course, I can quickly show you another thing, right? So you see, so here instead of using like ANSYS or FES software, so that I can quickly show you about how we can analyze this kind of a uniform bar. The length is given 0.5 meter, cross-section area and mechanical property and density, and which is fixed on 1M. So how can we do this? Basically, is we describe element, right? So that we can use this element matrix here, right? And discretize. I can describe into 2 elements or 1 element. Maybe this element 1, element 2, or maybe you can have a 3 element. Depends on how accurate you want to construct 1, 2, 3. So basically, there's a many infinite possibility to construct this kind of FEM model. So then the question is, how many elements will be good enough? What do you think? How many elements will be good enough? 1, 2 elements, 3 elements, or 100 elements? How many? This is a practical issue. In general, there's no general solution as far as how many elements we have. But in general, it's if your geometry is simple and you use very simple, find a very small number of elements, okay. But if you're very complicated, 3D structure with very complicated design, then the number of elements would be much larger enough to describe very complicated vibration problem. In general, that's the reality here. Yeah, but I told you this is something. I just show you. For example, here, we try to ask you first how to solve solid mechanical problem for this bar, and how to calculate natural frequency, and use 1 element to think. So that we already show you about the FEM, the right for this kind of a problem. Then you can simply assume only 1 element, and you have a loading force here, and then so that in this case we only see 1 particular thing, because this is bar. So one side it is U1, U2. This is fixed M, right? So in this case U1 0. So in this case, eventually we only get 1 equation. Linear equation solve this unknown U2. Okay, so this will give you very simple way you try to understand this kind of finite element. And of course, once you calculate the different displacement, you can calculate what? Stress and strain. So based on solid mechanics, we already calculate our displacement U1, U2. I can calculate our stress and strain. So this is I would say some important thing. So next is we can go to second issue. Why? We have to write our Kx here, and also the inertia minus omega n here. So this one we describe here. This one, once kind of vibration problem, we have this thing. In this case, we can get this kind of eigenvalue problem, determine our natural frequency, right? So that is something we can easily do. Yeah. Okay, so this will give you a very simple introduction about this kind of finite element. And then, of course, we can also repeat the same thing for torsion bar element, right? And then describe those kind of angular displacement as function of now this kind of two node. Basically, left-hand side, right-hand side node, right? And the angular displacement of arbitrary, this thing will be what? Function of this theta1 on left-hand side and theta2 on right-hand side. So this is what similar to what we described in the Feynman for bar model, right? For linear vibration problem. And of course, we can also calculate one describe this thing and then linear combination of this displacement, right? And next one, we can easily calculate our kinetic energy for the energy for this kind of torsion element. And then finally, we can also define our final element for the torsion element, our mass matrix 2x2 and stiffness matrix 2x2, and also force. Force matrix here is related to what? Huh? So this is actual loading. So if we have bar here, and our force is a continuous apply on this bar, so that eventually we need to determine what's the corresponding F1, F2. So this is given real loading force, and then using this kind of integration, so I can calculate our loading force from here to here. This is so. This is something quite important now for you to understand how we can determine M, K, and loading force vector. Okay, now I talk about two kind of elements, bar element and torsion element, right? And next one is a vibration of beam element. For the beam element, so that what we should do? What's the beam? Beam basically is a volcanic beam, and we have a loading, and then we cause some deformation, right? So in general, what we need to do? The key issue for this problem is we have what? We have this kind of thing. For example, you describe this kind of displacement W, and then what? Rotation. Rotation angle. So that in this case, in general, for the vibrational beam, it is linear transfer displacement and angular motion of the beam. So that is the important thing. We need to find displacement linear and angular rotation for the beam. Because this one, so that in this case, if you talk about final element, then we try to what? Then we try to describe for each end, you have two elements, well, one element, and then on the two sides. So in this case, I have a double one. This one node, node 1 and node 2. Element node 1 and node 2. And so here I have double one, so this is node 1, theta 1. This is double 2 and theta 2. And then so that for any kind of displacement in between or displacement W, the function of X, so will be what? Linear combination of this kind of four nodal, generalized nodal displacement. So that is the thing. So that here I show you the real thing. So that in this case, this W here, right, is a linear combination of this 1, 2, 3, 4, 4 generalized nodal displacement. Okay, so that's why in general, if we want to use this kind of polynomial function, right, to describe this kind of generalized displacement of the beam, then we have minimum degree of freedom. Minimum polynomial is a third. So we need A, B, C, D to describe the kind of a polynomial, and A, B, C, D should be what? Some special shape function which is orthogonal. Okay, anyway, I skip this thing, and eventually I will try to basically I skip this part and then eventually I show you we can define this kind of big element, right? Do the integration, calculate kinetic energy, strain energy, and eventually here. Okay, so this is the final element for a beam model. Okay, vibration of beam. We have our 4x4 mass matrix and 4x4 stiffness matrix. Okay. Any questions? So I skip a more complicated mathematics, but finally, after similar to the one-dimensional bar, so that we have to describe this kind of generalize the displacement as a nodal displacement, right? And then use this kind of kinetic energy and for integration, and eventually I can derive this kind of element, right? Matrix and K. But of course, the beam is more complicated. Again, emphasize, so that means relate to here. 4 degree freedom, well, basically is related here. So we have a left-hand side, W1, theta1, right-hand side. That's why it's 4x4. Okay, it's a 4x4 because we have a describe 2 nodes on both sides, left-hand side, right-hand side for the beam element. Okay. Okay, once here, then of course, the next one is so here, of course, we can show you more complicated 2-dimensional FEM for this contrast. So how can we do that? So this is more realistic now. So basically is we for this more this is a truss, you can say. If you learn our UG engineering static dynamics, so this is a truss structure, 1-dimensional bar element, so that once there's certain loading here, so that how can we try to solve this kind of problem based on F1 element? How do basically this require what? We have to look at each node, right? We define how many nodes for this kind of 3 more complicated structure. Here we have a node 1, node 2, node 3, node 4, right? We have 4 nodes basically. 4 nodes, right? And each node we have what? Described as nodal displacement. Each one the node displacement here is in the X, U1 and U2, so that here I tell you that we need to describe for each node, they have each nodal this kind of displacement, right? It being a 2-dimensional vibration problem, so you have a U1 in X direction, U2 in Y direction for each node, right? So that of course another important thing, composite is what? We also need to describe their the local coordinate and global coordinate. So here, this is more complicated now. So that basically where we have this is we call global coordinate system. Global. So capital X, capital Y, and then for each one, with additional local coordinate system. Here is small x here, and here, small x here. Is that so that for this kind of more complicated structure, more realistic, and then we different local coordinate system, and here, this is called local. That's here. Okay, so that then we try to this is the way we define this kind of a problem, and then of course in this case you see basically we define the global coordinate system, capital XY and local Y, and also those are displacement, now global and local. Capital variable is global, small letter for local. Y, and then in this case, for each Y, this thing for each node we can describe Y, U1, U2 as a linear combination, Y, compared with local and global. Yeah. And then of course, once you see it, then of course we can do the transformation from local to global coordinate system for our kinetic energy and strain energy. And then in this case, in general, we can find this kind of course, we can transform this kind of element matrices, Y, from local to global. In nature, you can assemble much bigger matrix now. Okay, so this is thing. So that in general, you can see now I show you this kind of in general, we can describe this kind of the general coordinate system for this kind of complete structure. Okay, and the same thing for the kinetic energy. Of course, we can also derive the same thing. Why? So previous one, if we read what Kij difference matrix, and we do the same thing to calculate our kinetic energy. Why? And then eventually we also do the transformation. Why? And then finally, I can try to construct this whole global equation motion based on finite element, and then we can solve this one in computer. Remember, this U can be very large for real product. Right here, I just show you very simple thing to describe the basic concept of FEM. And once you construct the whole equation motion based on finite element, and then next one is what? Impose bound condition. We specify the bound condition, right? And that is another quite important thing. Bound condition basically, for example, if you have this thing is structure, then basically, if you have this kind of structure, and then we need to look at how for each here, node 1, here displacement 0. So incorporate bound condition is something we artificially force certain kind of a displacement to be 0. So this is capital U1, capital U2 be 0. Right? So this is the boundary condition. Once imposed bound condition, next one is then we can solve the problem. Okay. Okay, I think we already try to give you this kind of example so that at least gradually you have a more idea. So next one, I show you one more example, vibration of beam. By simple support beam. So of course we have certain right our M and K now element for the beam, right? So that in this case we can simply, well, if you use one element beam, one element FEM model for this beam, so that in this case we have a left-hand side, right-hand side. So basically we have a linear and angular displacement on left-hand side, right-hand side. And because simple support, and what happened? Our linear displacement on both sides will be 0. So this is linear displacement now on both sides will be 0. Okay, so this will give you very simple way, and then with this one, then of course we can quickly show you this here. So that based on this kind of N and K for beam element, and we delete what? Because remember our bound condition show us this one is 0. Okay, so that means we have to delete this one and this one. Okay, So in message, we can reduce this kind of 4x4 table matrix into the 2x2. See, delete the row and column correspond this is our linear displacement. And displacement, you can see our vibration of this simple support beam become 2 degree feeder model. And then we can, of course, all of you can solve this kind of thing. So we can solve this kind of 2 degree feeder. Why? Simple thing and get our natural frequency, get lambda and omega. So that is something we show here. So that once you get this kind of eigenvalue problem, we can solve our lambda and then also omega natural frequency. So for this kind of 1 degree freedom, for this one element model, now I show you omega 1, omega 2. This is natural frequency for one element vibration of beam problem. Actually, we can compare with exact solution, right? So that the first natural frequency is 120, and then our exact solution is 97. So, do you have any question? Huh? Any? We have some more class. Your question you just ask, huh? And this, I told you, this is a FEN. Of course, you can use right away software, but still, you'll be better. At least a basic concept how computer try to do calculation. So basically, this is something give you some very simple introduction. You think about 1 hour, more than 1 hour. Describe how the commercial software can solve this kind of problem, right? For at least for sound mechanics and vibration problem. And so let me. Of course, I don't know if any of you have used this kind of commercial like the FEN software. Do you have any specific experience to use SolidWorks or use ANSYS so that of course for vibration problem basically you need to choose certain kind of what do you need? In practical like ANSYS or SolidWorks, so that the first is you need to really understand your mechanical structure, right? And then think about how you build reasonable mesh model, right? As I show you in this example, mesh model, so that your model will be not too simple, not too complicated. So that the first thing, if you use a commercial software, the first thing is you need to think about what's the reasonable number of elements you want to do the kind of build a mesh, right? So that because this kind of number of elements can decide how big the problem. You mesh too small, n too big, and then you solve much longer time, right? Because CPU time is time money. So engineer need to see how can we use minimum number of degree feeder, minimum number of elements, and then you can get the reasonable good prediction about your natural frequency, your vibration mode, and then understand if your design has any problem, right? So that is something important for you to make some proper judgment, right? And of course, I believe most of FEN simulation they do have some kind of benchmark to make sure that you can really try to do some good job. Benchmark is that just like this kind of cloud computing software, same scale. It's a benchmark problem. This is a benchmark. What's a good benchmark? That means that this is a well recognized solution. The case, right? You know the input give you all this kind of geometry and everything give you, and then you have a solution, and then you can validate, right? All this is existing, and then you see they give you all this input parameter for the particular mechanical structure in terms of a dimension, mechanical structure, and then I think I give you solution, simulation, and then show you. You see, they show you, okay, so this is the prediction of this kind of vibration of this kind of thing, and then try to show you here. Is that? So this is give you some typical demonstration about how to use because it is even the commercial free software online same scale you can do this kind of thing. Let me see if I can. You can sign up for this kind of and so what's good thing about cloud computing platform, Well, because here you have public project, have many people will share about their design of the thing, and then you can easily learn about the other people's the FEM model. Do you see? Can you see here that they do? Many people try to build their FEM, and then you can easily click here. Oh, I can look at their model for Mercedes-Benz. And then to see good thing is you can copy, right? Maybe you can try to download, open here, and then try to look at their FEM model. Right? Cloud computing is one good thing here. Oh, I can easily try to learn from the other people the design. Right? So this is, I would say, one of advantage of this kind of cloud computing platform, so that I can easily try to understand about more complicated structure. Wow, you see, if you want to build it, how long? Oh, take a long time. But the cloud computing, I can easily try to learn from the other engineer, right? And then try to think about this thing, and then try to maybe modify this one, and then quickly do simulation, and then for some selected problem. Doing that. So I just tell you, this is a pretty useful, I would say, now with this kind of online platform. Okay, so that you see here they do have so many different kinds of the model people try to create it and share with you. You will be surprised, but this kind of online cloud computing platform really, I think, have a good impact for, especially for our engineering students. Why, if you have no experience, and then if you can quickly try to learn from the other engineering from this kind of open source, the kind of platform, I would say it's very useful. Yeah. Okay, so that let me try to. I think we actually I will just try to show you this kind of thing. Let me show you one example, more with this example. This is I think this is one of pretty. Sorry. Yeah, this one. This is a real building. I know. I think some of you will go to industry, and our local industry still need a lot more related to building engineering. So that here, let me show you a building here. So this is a 14-story office building in Alaska. So that how can we build the model for this vibration problem? So that the key thing here is, of course, it can be a big project to really build a model. Why? But anyway, here I just show you example, so that basically first you understand what kind of material and structure used. This is steel structure, moment resistant frame with reinforced concrete, RC concrete. The length, geometry, right? And of course, they also have additional sensor, accelerometer, to do some measurement with 12 channel. And here, this is give you thing one. So here, see, they build this kind of using this kind of one-dimensional this element, the structural element to construct this kind of three-dimensional this kind of building model. So this is also quite useful for you to understand how using one-dimensional structural element to build more realistic this kind of a model for real industry. And then of course they also try to mount some kind of accelerometer to what? Because they can do some modeling using commercial FEM software, but still sometimes you need to get some measurement result to determine some of first validation of this kind of your model. Second thing, you may also use your sensor to determine some kind of unknown parameter like damping. Remember, we can easily build N and K, mass metric and K, same but for damping. This is one of the most difficult parts. So here I show you they have about 12 channels of accelerometer put there, and then in this case, you can see they try to base it on this kind of FEM model to build what? N and K. Both sides here, that's something is great. And then you using this kind of sensor, accelerometer, measure this kind of seismic, earthquake, see, and then do what? It can estimate this kind of natural frequency and also some damping, right? In this case, well, I can use this kind of experiment result to compare FEM. FEM here of MK, we can also there's no damping, right? So in this case, we can use this one to calibrate to improve our FEM model. Right, so that is something I think is an important way to leverage both computer modeling and vibration measurement. So that is something I think is important for you to understand this kind of important thing. Why, of course, here I already show you this kind of their FEM simulation result. Basically, you can see in general you have many this kind of vibration mode from lowest one, and then they can predict this kind of natural period of frequency. So there's a volt number, vibration mode number 1, 2, 3, 4, but they try to describe a little bit more detail on things, and they also try to look at this thing. So this is give you some, I think, quite important example of real engineering. So that now we compare about those kind of FEM result, right? And this kind of vibration testing result. This is from FEM model, and it's from experiment result. Okay, so it's I think quite close. FEM give you 2.2 seconds for this period, right? This kind of thing is about 2.19 and 2.23, right? So that and then I think basically I think the results show this kind of good agreement between FEM simulation and this kind of vibration measurement using some sensor. Yeah. Okay, and of course you can also visualize this kind of vibration mode. First, it's more dominant, the mode, right? And second mode, third mode. The higher the mode, it's more complicated. You see, it's like much more complicated thing. And then mode 4, the fourth vibration mode and fifth vibration mode is more complicated. This kind of vibration mode for Yeah. And of course, they sometimes they also try to do what? They for building engineering, what's the most important thing we want to think? Huh? We need to evaluate if a mechanical structural safety, right, of the building, so that in this case, once you build this kind of model, it's difficult for you to do testing to see, you find loading to see how big the vibration we can cause some collapse of the building. So they collect many earthquake data, and then with this kind of the history of the earthquake data, and then use what as a way to do the structural dynamic simulation in commercial software, which to double check if your building design can survive and make sure it can meet the building code. So this is one of quite important, right? So that they use this kind of earthquake data, right? Vibration data to what? To validate this kind of design of the building, and then to make sure you meet the kind of building code, right? So that this is I think one of important for energy, because if your design a problem, what happens? Many people die. So this is a very big issue about liability problems. So that if you didn't get a license, right? If you didn't get a license from like a Hong Kong IE license or something, you cannot design the building and this industry construction come to build this kind of building. So it's a kind in Hong Kong, we do have Hong Kong building code, huh? This is something you see in China, in US, so different countries, they reach in a certain building code, so that become quite important. Of course, for the building design, most likely don't use like ANSYS or SolidWorks. What do they? As I show you beginning, right? Most likely they have certain specialized software for building engineering. It's something I show you, huh? Remember, I just show you that thing. There's special FES software just for the building and civil engineering. This is something I have to let you know that. So that's why different industry that use this software. For example, in United States, they most likely so ETAP, what we want to use in the building industry in the United States, in China, here you see. If you're engineer, building engineer to design the building, and most likely you may want to use that special FES for that industry. ETAP are used in the United States for building industry. PKPN used in China. Is that so that you need to understand about this thing, so that most likely they have something, probably get some kind of validation from the government. Okay, this is more reliable. Yeah. Okay, so I think we run out of time. So I don't know, do you have any question? I believe this kind of thing is quite important, useful, right? Vibration engineering, I emphasize, we try to describe some thing, not only how we can use modeling, simulation, vibration experiment, and to work on vibration engineering, so that I do think it's something at least give you some quick review and show you some case study. I think